Now I do understand that we have gone off on a bit of a tangent. We started off looking at the fast inverse square root algorithm, but then we changed it in order to make it more accurate. And we replaced the idea of magic numbers with the idea of what I call magic lines. Now in the last video I showed you this equation here. I didn't actually derive it, and it turns out that the equation here is slightly wrong. So rather than having the value of a, it's actually a minus 1. So this is the correct equation here. Now this was noted by Timothy Morgan. So thank you, Timothy, for taking the time to have a look through the mathematics. So this is the correct version here. Now also what I want to do is rewrite the nomenclature a little bit, because it's slightly confusing in this format. The value for x is in effect our mantissa, which is mx. The reason I used the value x was that within the graphical calculator I couldn't put mx in, it wouldn't draw it out. It will only draw it out if you actually have the independent variable x. So this got carried over into the actual mathematics. So I've changed this back to mx, and also when we went to look at the approximation to our log to the base 2 1 plus x, we're going to use the linear approximation. Now the linear approximation I've rewritten in terms of the two parameters, in this case the parameter alpha and the parameter beta. Okay, so in effect here the alpha here is replaced by the beta and the a here is replaced by the alpha. So it's a bit easier to understand in this format here. So let's go ahead and we will look at the derivation of this equation, and a reminder that the derivation is was generated by Timothy Morgan. So thank you for that. So let's look at that now. So this is the proof of this equation here. We start off with the integer value for our ix, which is L e plus b plus mx. L for a 32-bit number is 2 to the 23. This is the exponent, the bias, and the mantissa. Our floating point number can be written in this format here. We can take the logarithm of both sides to give us this here. We're going to take an approximation for the log to the base 2 1 plus mx. This approximation is going to have two numbers. It's going to have a y-intercept, which in this case we'll call beta, and it's going to have the gradient, which we can call alpha. So it means that if we were to replace the log to the base 2 1 plus mx here with this value here, we're going to get the log to the base 2 of x is e plus alpha mx plus beta. Now the only interesting part here in this mathematics is really the next line. The value for ix is fixed. This is how we generate the ix, but we're going to be writing this in terms of the approximation which we've generated, which is alpha mx plus beta. So we've got to get the alpha mx and the beta into this equation here, but of course it has to remain exactly the same. So in effect we're going to have the ex plus b plus mx, and then we're going to be adding in the value of beta. So if we add in the value of beta, we're going to subtract it back off again in order to ensure that the equation remains the same. And again, whenever we add in the value of alpha mx, we're going to have to subtract off the value of alpha mx as well in order to ensure that the equation again remains the same. So it means that we can rewrite this thing here in this format here. So you can just take your time to have a look through and convince yourself that this line is correct. And then of course we can replace the ex and the alpha mx and the b with the log to the base 2 of x. So we replace that down here and the rest of it remains the same. So we can then rewrite this in terms of log to the base 2 of x, and we get this term here. And of course we've seen that we go through the generation of this inverse square root, and if we can rewrite this inverse square root in this format here. And then we then make this term here, which is log to the base 2, which is, we've found out, is just equal to this term here. Okay, but in this case it's going to be the y value, okay? And in the right hand side it's minus a half times the same thing again, but it's the x value. But in this instance here, the my and the mx, well, they're actually the same values. There only is one input value for the mantissa, and that is the mx. And we can rewrite it in this format here, and again we can transpose the equation to get the final value here. Now again, this is a lot of me kind of talking my way through. If you're interested in the derivation, you can stop this video and have a good look at it yourself. I wasn't intending to go through all of the mathematics in this detail, but because I had made a mistake in the derivation of the original equation, I thought it was maybe good just to go through and clarify this. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.